Hi, I'm Jason Del Rosario, and I'm studying electrical engineering. And for the summer, I worked with the UMDES group, or University of Michigan's Discrete Event Systems group, where I was supervised by Professor Stefan Lafortune and PhD students Yi-Chin Wu and Eric Dalal. I began my summer by familiarizing myself with discrete event systems, or DES, which are essentially systems of states, events, and transitions. And as you would recall in physics, functions are usually time dependent, but in DES it's event driven. And here's a simple example. Typically, discrete event systems are represented in a graph similar to a flowchart, which describes the machine's functionality, where states point to another state, to itself, or to multiple other states through transitions which are caused by certain events. And here's a representation of what just happened. As you noticed, when I waved my hand, an audio file of a laughing noise is executed. And when I put my hand down, the audio file stops. I worked on two projects this summer. One is the TRW project, and the other is the Discrete application, which is what I was using earlier to represent the DES. And I'll pass it on to Eric to talk about that right now.
Hi, my name is Eric Dalal. I've been working with Jason this summer, and we've been working on a program called Disuma. So basically, this is a graphical user interface, which allows me to create new automata, so represented with states and transitions. And then using these, I can do various operations on these automata, like, for example, accessibility or co-accessibility. So this one will tell me nothing's whoops. Submit. And it has no co-accessible parts. So that's the correct answer. And so there's a bunch of other operations like this, and what we've been doing here is basically fixing up the graphical user interface and fixing some mild bugs that existed with the program, such as, for example, the marking of states. So for example, if I do this, now it works. Before, it wouldn't make this state marked. So this is what we've been doing, and it's working pretty well now, and we should have a new version up in a couple minutes, actually. So there you have it.
Hi, I'm Stefan Lafortune, a professor in the EECS department. So we call our group the UMDES group, where DES stands for Discrete Event Systems, which is our area of research. And I think you can guess what U and M stand for. And so in this group, we look at dynamic systems where the transitions are what Jason was involved in the summer was related to, number one, our software infrastructure that we've developed for analyzing discrete event systems. And the tool is called Disuma, and Jason was involved in testing a new version of Disuma that is about to be released. We make it publicly available on the web, and it's used worldwide. I should say, the second phase of the internship in a specific project that we have been working on for quite a while now, which involves modeling an actual software program for passive entry in automobiles. When you just have the key fob in your pocket, you approach the car, and then you can just open the door. And it's actually a demo system that was, source code was given to us by an automotive supplier in the area, TRW Automotive. And we use it as a learning example for us for how to model, abstract away from the source code to a mathematical model that we can then analyze and verify if there are any bugs in the software, essentially. So it is a bit of a challenging exercise because we are going from the source code and abstracting all the features that are relevant to the execution of the program so that we can detect bugs. And we have scalability challenges in terms of the model grows, in terms of very large state spaces, and then therefore doing the analysis is actually pretty challenging. It may seem very simple just to have the key fob in your pocket, approach your car, and be able to open the door, but there's actually thousands and thousands of lines of software code that run in your car just to implement that system. Just to give you a scale, it was an effort that took more than 1 year to one programmer to develop that program that was just a demo system, not even production system.
The goal of the TRW project is basically to use a more formal approach, a model-based approach, to verify the correctness of the code. So the software is designed to automatically lock or unlock the door when the driver is. So the ultimate goal is we want to reverse the process by building the model first and verify the correctness of the model by using discrete event system, discrete event control theory, and then after verifying the correctness of the model, then we start building the software from the model. So, but in this project, our first approach is to reverse engineer and build the model from the code, and to verify whether the code is correct or not. And then if it is not correct, then we want to reverse back to see where the error is. So our first approach is to build automaton model from the software. So first we build basic automaton that is responsible for all the main features in the software. For example, as you can see here, so this automaton model begins at idle state, and when there's a PS event, which means that the passenger, the passive door, I think it's called passive door switch is pressed, then it will go, it will start a control statement to check whether this event is true, and then if it is true, then it will set this command to unlock all door and then start doing the external scan. So we first built this basic automaton to capture the features, the main features in the software. Then we also built a variable automaton to capture how variables change values according to the exogenous event, or like the setting, the updating, changing variables internally in the software. Then we obtain the full model by doing parallel composition. Actually, we we introduce a new parallel composition to capture the real behavior of the software. That is, we only allow exogenous events to occur in the real state in the system, allow the variable checking events in other states.
Okay, so my name is Stephen Lanham. I am a recently graduated undergraduate student, and I've been working on the TRW project under Professor Lafortune. My role in the project has been to develop a way to dynamically create the parallel composition space of all these automata, which is a representation of running each of these finite state machines in parallel. And so the parallel composition is an operation which requires knowledge of all the component automata simultaneously, and knowing information about events when those are allowed to occur in each of those machines, and then how those events interact between machines. You can basically create a state space as a representation of all possible events that could occur in any of these composite states. So what we're interested in knowing there is, how can we explore that state space dynamically? It's far too big for us to keep it to represent the entire thing in memory at once. So how can we explore that state space dynamically and understand situations in which we enter an area of the state space from which we cannot recover, and that, for our purposes, is considered a blocking event. The usefulness of this is that when blocking events occur, the underlying automata are not able to recover into some sort of default state. So if you have multiple processes running in parallel, you basically see a deadlock or a live lock condition. So the way we've been doing that is dynamically generating the state space and then performing a depth-first search through that state space, looking for these events. We initially perform a depth-first search in the forward direction to understand the subset of events that are accessible. Then we perform a depth-first search in the backward direction to understand which events are co-accessible, meaning which events, from which states we can get back to the original or the initial state. Then the third search we perform is to analyze, with knowledge of what states are accessible and co-accessible, we analyze the events which lead us into these blocking portions of the graph, and that's how we create, or we identify the situations where we enter live block and deadlock.
Prior to this summer, I knew little or nothing about discrete event systems, but after working with Professor LaFortune, Yi Chin Wu, Eric Dalal, and Stephen Lanham, I definitely knew more about how they work and what they're used for. Before, I've only had one semester of programming C++, but after this summer, I've definitely expanded my knowledge in that area. This summer also made me think of the possibility of grad school, and systems engineering is definitely something I'm considering. And there you have it. That's my summer.